Welcome. In this video, our goal is to solve a challenging exponential equation using a clever algebraic technique. By the end of this session, you'll be able to solve complex equations by transforming them into a system of inequalities. The equation we will tackle is akx plus ak2x plus bk2x plus b2x equals ab times the quantity ax plus b2. This equation might look daunting, but we'll break it down step by step using the same solution method provided. We'll start by simplifying the problem with a substitution. Our first step is to simplify this expression using substitution. Notice the recurring terms a to the power of x and b to the power of x. Let's make a substitution to simplify the equation. We'll set u equal to a to the power of x and v equal to b to the power of x. Since our bases a and b are positive, a to the power of x and b to the power of x will always be positive numbers. This substitution helps us rewrite the original equation in a much more manageable polynomial form. Let's see how our substitution transforms the equation. A to the 3x becomes u cubed, a to the 2x becomes u squared, b to the 3x becomes v cubed, and b to the 2x becomes v squared. On the right side, a to the x times b to the x becomes uv, and in the parenthesis, a to the x plus b to the x plus 2 becomes u plus v plus 2. Now let's expand the right side to get a clearer picture. Expanding the right side gives us u cubed plus u squared plus v cubed plus v squared equals u times u, which is u squared v, plus uv times v, which is uv squared, plus uv times 2, which is 2uv. Our goal is to find the values of x that make this statement true. Solving this polynomial equation directly can be difficult. A powerful strategy is to transform it into a comparison or an inequality. We will now move all terms to one side of the equation. Let's subtract the entire right side from both sides of the equation. This gives us u cubed plus u squared plus v cubed plus v squared minus the quantity u squared v plus uv squared plus 2uv, all equal to 0. Now, let's rearrange the terms. We'll group the cubed terms together and the squared terms together. By rearranging the terms, we get the quantity u cubed minus u squared v plus v cubed minus uv squared plus the quantity u squared minus 2uv plus v squared, all equal to 0. This rearrangement is very helpful because each group can be factored. From the first group, we can factor out u squared, leaving u minus v. From the second group, we can factor out v squared, leaving v minus u. And the third group is a perfect square, u minus v squared. All of this still equals 0. We're almost there. Notice that v minus u is the negative of u minus v. We can rewrite the second term by changing the sign. So we have u squared times u minus v squared times u minus v plus u minus v squared equals 0. Now, every term has a common factor of u minus v. We can factor it out. Factoring out u minus v gives us u minus v times the quantity u squared minus v squared plus u minus v, all equal to 0. This gives us a simplified form, but there's a more elegant and instructive way to solve this, which we will explore next. Let's revisit our substituted equation and see how we can use inequalities to find the solution. The core idea is that we can derive two separate inequalities that when added together produce our equation. The only way the equality can hold is if it holds true for each individual inequality. Recall our equation after substitution. Let's group the terms differently this time, separating the cubed terms from the squared terms. We can rewrite the equation as the sum of two parts. First, u plus v query, and second, u plus v query. On the right side, we'll group the terms uv, uu plus v, and 2uv separately. Our goal is to show that the left side must be greater than or equal to the right side. Let's tackle the first inequality. u plus v plus must be greater than or equal to uv times u plus v. This inequality is u plus v plus golden u plus v. Let's prove it is true for any positive u and v. Using the sum of cubes formula on the left side, we get u plus v times u squared minus uv plus v squared. So the inequality becomes u plus v u squared minus uv plus v squared greater than uv u plus v. Since u and v are both positive, u plus v must be positive. This means we can divide both sides by u plus v without changing the direction of the inequality. Dividing by u plus v gives us ugrect minus uv plus vgrect, Cortez, gradually uv. Now, subtract uv from both sides. This simplifies to u minus v, quantity squared, is greater than or equal to 0. This statement is always true for any real numbers u and v, because the square of any real number is non-negative. This proves our first inequality. Furthermore, this inequality becomes an equality, or a true equation, only when the expression u minus v squared is exactly 0. This happens if and only if u equals v. So, we've shown that the equality u plus v equals u plus v holds if and only if u equals v. Now let's establish our second inequality, this time focusing on the squared terms. We need to show that u squared plus v squared is greater than or equal to 2uv. This is our second inequality. Let's prove this inequality. We'll start by subtracting 2uv from both sides. Subtracting 2uv from both sides gives us u squared minus 2uv plus v squared is greater than or equal to 0. This expression should look familiar from the last inequality. Indeed, u squared minus 2uv plus v squared is the expansion of u minus v squared. So, our inequality simplifies to u minus v squared is greater than or equal to 0. Just as before, the square of any real number is non-negative, so this inequality is always true. It's a fundamental property of real numbers. For the equation u squared plus v squared equals 2uv to hold true, the expression u minus v squared must be 0. This only happens when u equals v. So, we have also shown that equality in u squared plus v squared is greater than or equal to 2uv holds if and only if u equals v. Now we have two established inequalities, and we know the conditions for equality in each. We have u plus v cap greater than u plus v, and u2 plus v cab greater than or equal to uv. The beauty of this method is that we can add these two inequalities together. Adding the left sides together and the right sides together gives us u2 plus v plus u2 plus v2 minus 1u plus v plus 2uv. Let's factor the right side. We can factor out uv from the two terms on the right. This gives us uv times the quantity u plus v plus 2. Take a moment to look at this result. Does it look familiar? It's exactly the equation we started with after substitution, but now it's an inequality. We have shown that for any positive u and v, the left side is always greater than or equal to the right side. Our original problem, however, states that they must be equal. Therefore, the only possible solutions are those for which the equality holds. For the equation to be true, the inequality must be an exact equality. So, we need to find the conditions under which equality holds true for both inequalities simultaneously. This is the crucial step in our solution. We established that the equality u plus v equals uv plus v is true if and only if u equals v. We also established that the equality u plus k v2 equals 2uv is true if and only if u equals v. Since our overall equation was the sum of these two inequalities, the only way the total sum can be an equality is if each individual component is an equality. This means that both conditions must be met at the same time. Therefore, the only possible solution is the one where u is equal to v. Now we can use our original substitutions to find the value of x. We have u equals v, and we know that u is a to the x and v is b to the x. So, we must have a to the power of x equals b to the power of x. We can rewrite this by dividing both sides by b to the x. Since they both have the same exponent, we can write it as the quantity a over b to the power of x equals 1. For any non-zero number, the only exponent that results in 1 is 0. So, we must have x equals 0. Let's recap. We've shown that if a solution exists, it must be x equals 0. We've also proven that x equals 0 is a valid solution. The solution set, denoted by S, is simply the single value 0. Let's summarize what we've accomplished. We started with a complex exponential equation. Our initial equation was a to the 3x plus a to the 2x plus b to the 3x plus b to the 2x equals a to the x b to the x times the quantity a to the x plus b to the x plus 2. We used substitution to simplify it into a polynomial in terms of u and v, where u equals a to the x and v equals b to the x. This gave us u cubed plus u squared plus v cubed plus v squared equals uv times the quantity u plus v plus 2. Instead of solving the polynomial directly, we broke the equation down into the sum of two inequalities. We prove that u cubed plus v cubed is always greater than or equal to uv times the quantity u plus v, and u squared plus v squared is always greater than or equal to 2uv. By adding these two inequalities, we found that the left side of our simplified equation is always greater than or equal to the right side. This means that for our original equation to be true, it must be the case of strict equality. For this to happen, both of our original inequalities must also be equalities. This condition forced u to be equal to v, which allowed us to solve for x. Requiring equality led to the condition u equals v, which gave us a to the x equals b to the x, and ultimately, our solution x equals 0. This problem is a fantastic example of how transforming an equation into inequalities can be a powerful and elegant way to find the solution. You've now learned how to apply this technique to a complex exponential equation. Great work!